My name is Kyle Perisher. This is a follow-up, the CTF challenge for Halborn cybersecurity. And although this wasn't required, just wanted to show some extra effort here and kind of re-emphasize what I put in the report. So this is my report on Solana smart contract challenge in Rust for Halborn security. Date of engagement, April 20th to April 26th. Here I provided the repo to the direct challenge itself. Here you can find a summary overview, index of where things are at. So if we go down here, all right, so here under the assessment summary and findings overview, this chart right here is just to give a reference of the for the vulnerabilities that were found. 1 is critical and 2 is high. Although when we go further into it, you'll see how the critical one leads to the high vulnerabilities. And although I just listed 2 there, with that 1 critical vulnerability, it's just a matter of imagination, you know, and you can add numbers to this. But for this report, 3 vulnerabilities will be explained. And so the security analysis, the segment faults lead to multiple critical vulnerabilities. Like I said, this risk level is critical. This remediation date right here is more so a reference of the timeline of which it took me to understand and really lock in the concept of what was going on and figure out a solution to what was going, what that vulnerability was. So the other 2 vulnerabilities I was able to identify is account type and account/type confusion, and arbitrary signed program invocation. Moving into the findings and technical details. Seg fault in time crate leads to potential memory corruption and remote code execution. It's also not just in the time crate, but it's in the chrono crate. In the chrono crate in Rust, you can find it on crates.io. But basically this chrono crate, it handles a time and date function, and due to Solana working off a proof of stake model and also proof of work, and they're joined in the consensus mechanism. And I believe I provided reference links to the white paper as well. You know, because it's so crucial to note the date and time. This vulnerability breaks the functionality of how Solana is supposed to work. So obviously that leads to a lot of serious critical vulnerabilities, because in security, all it takes is an attacker to find one vector. Usually it's a numeration, and this would be the numeration, the segment fault in time crate, in the chrono crate. Briefly note the technical description. So segment faults may occur in Unix operating systems due to difference in dangling pointer in specific circumstances. This could happen via an environment variable being set in a different thread than the affected functions. This could occur unbeknownst to the user, notably in a third party where the user might not know right away that a package is no longer being maintained by its author. And that's a reference to the chrono crate, because it's not being maintained anymore. The recommendations after doing research was to just fully use the time crate, because the time crate pretty much does the same functionality, but it does have a patch. is the screenshot of the fuzz test and the audit test that I did on the code itself. You can see here that it's the time crate, and this is the version, and it gives you the ID of the security vulnerability report. It's marked as RustSec 2020-0071 and RustSec 2020-0159. And these also have associated CVSS scores as well. So similar in Linux, if an attacker can alter the time date in a system, then they can really do a lot of dangerous things. Importantly, what they can do is completely mitigate security, really hide themselves, and add a lot of persistence. And here I go into the two other vulnerabilities. Account confusion vulnerability lies in feeding the contract arbitrary data via an account. So in Solana, an account is, think of it like a MIDI controller coming from like a musical background, because I come from a musical family. So a MIDI controller can be programmed to send other different types of data. And so a wallet address basically gets fed into a series of functions or a series of instructions. And that wallet address is basically a smart contract that in that smart contract then performs a series of functions. So you're basically chaining together different functions in order to pull together what this main smart contract is doing. The vulnerability here lies feeding the contract arbitrary data via an account. For example, a malicious contract could call the contract to withdraw tokens. If said contract created a function to write itself to an unprotected or not verified account, that's also referencing to missing ownership checks. You're creating a struct of config. This pub right here means that it's when another smart contract calls out to this smart contract, it can see this. And so here you're setting admin to the public key. You're setting your fee. U32 is referencing how many bytes, like how much the fee is set to. And then the user account, the user count. This is how much the user is charged for fee. And here we have the other public struct, which is labeled user. User underscore authority is passed through and checking the public key. And then here's the balance. So it's the other code. I won't go into detail here. I tried to add it up. I tried to add a lot of comments to like explain it out. But the solution here is basically to add a helper function and assign a if statement returning an error if the account type doesn't return with the right ID. So you're basically setting a unique identifier for that account, and in the smart contract, when you're coming from the development of the smart contract, setting an ID, a unique identifier, will allow you to then create a helper function that has a if statement that says if this account ID is not present or it doesn't match this ID, then return an error. And so this prevents account confusion for different account types. So that would prevent this vulnerability from being exploited if this was in the code, in the smart contract. The third vulnerability that I emphasize here in the report is arbitrary assigned program invocation. Working similar, I briefly went over it with like setting an environment variable. So you're basically sending garbage data within your call to the contract. You could also use a environment variable to perform a remote code execution type of attack. The best way I can explain this is like in Linux. I like to explain this in terms of, say you want to do a curl request. You're doing a curl request to a web server that accepts input and it pushes back out output. So, and if this server, say, is MySQL, and it allows you to upload as well as sending data, that's even more dangerous. But the exploit here in this reference that I'm referencing to, you could send a curl request to that server that basically it computes it and decodes it. So if you're sending a curl request, you're gonna have to URL encode something, like URL encode it if you're trying to feed it arbitrary commands. And so in this example, arbitrary assigned program invocation in Linux, you could basically base64 a netcat command, and you send that netcat command in base64. You pipe that into a base64, and you give it a TAC D, which decodes it. And then following that, you pipe that into bash. And so because the server is taking in the data and it's reading it, it's going to decode it from URL and then see that it's base64. And then it's going to decode that base64 into a bash shell, into a bash terminal. And so that would be a way of remote code execution, which in this case, what I'm trying to compare it with is similar to how this arbitrary assigned program invocation attack works, where you're basically circumventing any security checks, whether it is obfuscation or whether it's taking advantage of the fact that you can run whatever you want. If that environment variable gets passed through with no checks, you can run whatever you want. You can steal tokens. You can make yourself the owner of the smart contracts. You can basically perform like a proxy attack and set a helper function to basically intercept any requests to that actual smart contract. So it'll go to the malicious smart contract rather than the actual intended smart contract, because again, there's missing checks on the program itself. There's missing checks on the ownership. And because of the vulnerability, the root vulnerability being segment faultation, then that leads to memory corruption. So you can see how this one attack basically just opens up the floodgates to really, it's up to the attacker's creativity, honestly, because there's a lot of different ways that you can spin this. But here you can see the goal of an attacker is to try to get all in one fell swoop. Like I said, sometimes only needing to exploit 1 out of the 4 exploits, referencing to the common exploits and pitfalls of Solana. The most common being missing ownership checks, missing signature checks, integer overflow and underflow. That's also that memory corruption thing I was mentioning, and then arbitrary assigned program invocation. Here I go into technical description. The example here is the invoke instruction is used to call out to foreign programs to perform certain functions. For example, invoking SPL_token program to transfer funds between token accounts. You'll also see this reference as cross-program invocation, or CPI for short. Solana by design requires that a program invokes by an instruction set. An instruction set is basically a description of listing the wallet addresses. Because going back to what I said, the wallet addresses are basically links to accounts, or all the accounts that then in their instruction set perform the functions detailed within that smart contract. So you can see the big vulnerability there. Therefore, it's supplied by the user, being that the user is able to input an arbitrary program account. It is crucial that you validate, always validate the owner of the smart contract, because if you can't trust it. So yeah, so that is the technical description of the third and final vulnerability. I did provide some screenshots here of examples of the insecure code, and then the fixes or the mitigations for that. It's important to note that as of the SPL token version 0.1.5, Solana introduced a hard-coded check to ensure all SPL invocations can only use the real SPL program as program_ID. So that's similar to the helper function that I mentioned as a mitigation for the account type confusion vulnerability or exploit, where you basically assign an account ID. That helper function is going to check for that ID, and if it doesn't match that ID associated with that account, then it's going to fail, and it's going to error, and it's not going to function. And so that is the same here, but as specified as a program ID. Okay. Yeah, and that last part, this doesn't provide mitigations when calling programs other than the SPL, or that are using outdated SPL versions. Anything before version 0.1.5 is affected by this. Here in the fuzzing section, we go over a general fuzzing description and some tools that are used, like libfuzzer, cargo fuzz, the fuzzer sanitation. It goes into sanitation coverage. Here I list the affected functions. Here in the time crate, you have the UTC offset, more specifically the local offset at, try local offset at, current local offset, try current local offset, now local, try now local, at UTC, and now. All time functions, very, very, very important and crucial for proof of stake and proof of history. Here in the automated testing, we go over we go over security scanners, similar to such as cargo audit, which back in this screenshot here, this was from doing the cargo audit, and this is what it returned. So using that cargo audit tool helped narrow down the error of where the vulnerability lies. And I provided links, hyperlinks to all of the words here highlighted in green. They all have hyperlinks, or they should. Here you have the ID number for the security announcement, and specified the package. And you can see code execution, memory corruption. Here I provide another screenshot of the affected crates. And yeah, so